All right, so tonight we're going to be covering the idea of clustering, looking at two main clustering algorithms in particular. And this kind of marks the first time we've seen unsupervised learning. So far, everything we've learned with regression, with classification, that's what's known as supervised learning. And I'll go into the difference between the two here in a second. But tonight we're going to be looking at unsupervised learning. And the two algorithms we're going to be looking at are k-means and hierarchical clustering. So here's kind of the difference between unsupervised and supervised. Supervised learning, we have the labels. So for classification, we know what classes each of the data points belongs in, and we just try to train a model that can accurately model and predict that. In unsupervised, we have no idea what data points are in which classes, even how many classes there are, or what the classes represent. We have just a bunch of kind of unstructured data points, and we're trying to develop some kind of meaning or order or grouping amongst the data. Here's another kind of overview of unsupervised learning. So you basically provide it with unlabeled data, and it finds similarities within that data to create groups. And so clustering can be used for like market segmentation. So if a company has a bunch of customer data, they can kind of run an unsupervised learning model on it and figure out different segments of their customer base, and then target those groups specifically depending on their individual attributes. The other use of it is anomaly detection. So to detect hackers in a network, basically being able to look at traffic online, basically any kind of activity online, and to notice things that are kind of separate from the majority of everything else and things that are abnormal. So to start with, we're going to talk about k-means clustering. This is probably the easier of the two to kind of understand. To start off, we're just going to make some data here. We're going to have two features so that we can plot it in 2 dimensions. And let's take a look at it here. So we just have 10 data points. They're kind of all spread out. They don't have any class already. So we're going to try and group them. So to do this, we import k-means. And actually before that, to give you an overview of how this works. So basically we start off by, let me find a good, okay, that'll work. Okay, so you start off by picking some value for k. So k is going to be how many groups you want to divide your data into. We'll get into kind of how you can choose a value, but that's kind of something you have to provide it. So we're going to start with 2. So you basically pick 2 random points somewhere in your data space, and then you look at every other point, and basically, actually that should be a different color. Let's do this one, be red. All right, so then you look at every other data point, and whichever of these 2, they're called centroids, a data point's closer to, will assign it that class. So you can also kind of think of it like, since we only have 2, you know, there's basically a line between them. Anything on this side is going to be red, anything on this side is going to be blue. So you kind of would connect all of these. So all those are red, and then these 4 would be blue. And then once you've done that, within each group, so within the blue, you're going to take the average of all the points and create a new centroid. So somewhere in the middle of all these points would maybe be like here. And then for the red, you know, that's maybe like up here a little bit. And then we basically repeat the process. And that keeps going until you don't move the centroids anymore. So in the curriculum, they actually have a really good GIF of this. Let's see. So this will kind of show you how the algorithm works if it'll load. Let's do this. All right, so it's picked the centroids. It's those green spots. It's assigning all the data points to one of the centroids that's closest. Once it's done that, the centroids move towards the center of all the points that it was connected to. And then this keeps repeating. As you can see, some of the points will change groups, basically until they aren't going to move anymore. And there we would have 4 clusters. And this would be if we put a K in for the K-means. So that's the basic idea of what it does. To use it in Python, it's really easy. It's also from sklearn. So we're going to start off doing 3 clusters. So we pass in n clusters equals 3 here. And then we're just going to plot it and then kind of color them different colors so we can see the division. So the black dots are where it put the centroids. You can get those from the cluster centers here. And then the other points are our original data points, and then their color corresponds to whichever class they were assigned to. So in this case, we had 3 different groups, but you can see if we change this, if we go down to 2 clusters and fit it, the centroids are in different locations. There's a little bit different assignment of the points to the different clusters. So you may be wondering, well, how can I, know which K value is the best to choose? Well, I guess first of all, here you can also get the predictions off of the cluster object here this way. I'm just calling predict and passing in your data. So actually, we'll first look at kind of a larger data set. So before that was only 10 points. But what if you have 1,000 data points? It might be a little bit more difficult. So this is where the elbow method comes into play. This is how you can find an optimal value of K. So what you basically do is run through from 1 to whatever value you want to try out for your K values. You'll build a K-means model, and then the metric you want is inertia. It's basically a measure of the variance within the clusters. So the more points are further away from a centroid, the higher that variance is going to be for that point. So you want the inertia to be minimized. So we'll go ahead and take a look at this plot here. Let me actually go back out because I can't see the whole thing. So you usually get kind of a curved L shape or an elbow looking graph like this. And basically, the best way to choose a K value from this is you want to look where the bend is. So you want to look where the drop, so this is our inertia here, or distortion, you'll see sometimes too is what they have on here. But you'll want to basically look for where the inertia stops decreasing by a lot. So we can see from 1 to 2, it drops a lot, from 2 to 3 a lot, from 3 to 4, a little bit less, and then basically from 4 onward, it's a lot smaller each time. So you basically want to pick one of the values in this area, basically where the elbow would be if this was your arm. So for this case, it's not obvious, one particular value. You could probably do 3 or 4. So you can kind of try both out and see which one might be better. So let's go ahead and pick 4. And just like before, I'll plot the centroids. I don't know why it gets cut off. Okay. So you have the centroids, the black dots, and then the clusters that all the data points got assigned to. So that was with 4. We can just see with 3 what happens. So that one's maybe not as good because you have all these green points. It's kind of really spread out. But when you go to 4, everything's kind of in a nice radius around the centroids. So that's basically K-means clustering. Before we move on, does anyone have any questions? Or does this just make sense?
Yeah, Matt, for the elbow plot, you're using the model where, oh, never mind. I take it back. Never mind. I don't have any questions. Sorry.
All right, yeah, it's basically just fitting a new model for each value of k in our range, and then it's getting that metric, the inertia off of it. All right, so that's k-means. Now we'll talk about hierarchical clustering. So this is a little bit different of an approach, but just like before, we'll start with kind of the same data set. Basically, what hierarchical clustering does is it'll start off either large scale or small scale and kind of build up or down from there. The most common is from small to large. It's called agglomerative clustering. So basically, it'll find the 2 points that are closest together, so these two. Then it'll find the next 2 points that are closest together and group them. And it'll keep repeating this. So it looks like this one's closest to this one. So we'll actually make this a group and combine them. And then maybe these get combined, and that's a group. And then this becomes a group, and then maybe up here, and then this one, and then this one. So you end up with like a hierarchy of grouping. So at the very bottom level, you'd have basically all the individual points as their own clusters. But then you move up to where you have 2 in a group to 3. And so you have all these different layers of different numbers of points in the clusters. So
Matt, how would that one work if there were 3 groups?
what do you mean if there are 3 groups?
Like, well, we ended up with 2 groups, or is that just with these points, it'll always end up in 2?
I mean, you always end up basically at having like at a point where you're at 3 groups, and then a point where you're at 2, and then 1 at the top.
Okay.
Because like, let me just redraw this.
I think, Andrew, are you talking about the number of features?
No, see how we got 2 big blobs there? Would we ever end up with like 3 big blobs? Or does it always?
You mean?
I guess each time we add a point, does it have to go to an existing group?
Yeah, so I think you usually do have, like you're gonna see in a second, you basically get like a tree-like diagram where it breaks down like this. So it does split off by 2 each time.
Okay.
Wouldn't it be just one group? Because at the last grouping would be the grouping of these 2.
Yeah,
there's gonna be one last circle.
The one at the top, which is like up here.
Mm-hmm.
All right, you'll see the tree here though in a second. I might have it make more sense. So let's go ahead and import it. So like I said, there's 2 different ways. Either start small, you know, every point is its own group, then do groups of 2. That's agglomerative. The other way, I forget, is it, I'm not sure it's on here, but it's basically the opposite. It'll start off by making everything one cluster and then kind of segmenting and breaking it down, going from large to small. But you'll usually see this way. So let's go ahead and fit it then. We do it the same way. We're going to plot it, and I probably need to import the library first. And there we have it. So in this case, I think the default n clusters is 2. So that's what it did here. But I can put in different values here, just like on the k-means. So I can do 3, and it'll give me 3 different clusters. It will group differently than k-means, even if you have the same number of clusters, because it's 2 different algorithms, so they usually have different answers. And then off of this, you can check the labels. So basically what each data point, which class it belongs to. So in this case, we have 3 classes, so 0, 1, and 2. So the cool thing with hierarchical clustering is that you can kind of visualize what's called a dendrogram. It's that tree-like structure that looks something like this. So this is basically how it did that grouping, starting from small and going up to the top. So these are like the IDs or indexes of all of our data points. So at the very bottom, they're all their own group. But then as you move up, it grouped these 2 together, then these, then those two groups, then that one, and then that one, and then overall making it one group. So when looking at this, instead of doing the elbow method, you usually want to look at a dendrogram, and to determine the number of splits that you want, you usually want to find the area where you have basically the largest distance between segments. So in this case, it would probably be between here. If you draw a line across, we have 1, 2, 3, 4, 5. So that would tell us that 5 is probably going to be our best bet. So that's actually what I put in down here. And we'll go ahead and run that and take a look. So that did it into 5 groups. We only have 10 data points, so these 3 have only 1. But if you look at kind of the radius, it's pretty small around each one. We could also look at 4. So then we can look at that larger data set as well with 1,000 data points. So the problem here is that when you have that many and you try to do the dendrogram, you're going to get this in a second. Because you think it has to do that for each one. So you'll get this mess where you can't really see anything. I mean, it could enlarge the figure, but there's so many data points, this method isn't really going to help you. So it is a little bit harder to find the optimal number of clusters with the hierarchical method. You can rely on the elbow method, but there are some ways to kind of narrow down. So one thing you can do is check how many samples are in each cluster. In the case of like market segmentation, your company might want to have, X number minimum of customers in each segment. So like say 100 or, 1,000 or something. So in that case, you want to make sure that your smallest cluster is bigger than that minimum. So to do that, you can fit a clustering model here. And then kind of a neat trick to get the counts of all the labels is to just use pandas, pass it in as a series, and then use the value counts off of it. And there's our 3 classes because we passed in clusters equals 3. And so we can see the value counts there. But if we increase this, then we have one that's only 169. If we take it up to 10, then they get much smaller. So that can sometimes lead you in a direction where you can choose a number of clusters where you meet like a minimum number in each group. So that's one option. You can also look at the statistics of each cluster. And you could do this for k-means or for hierarchical. You can basically see what the underlying statistics are for each group and how they differ. So we will go ahead and make a new data set here, fit a clustering model with 5 clusters. And then I'm going to make a data frame, which will basically get the mean value for each feature in each cluster. And then we'll display it in a data frame. So for each of our clusters, each of our groups, we can see our features here at the top, and we can see the mean values. So from this, you can imagine if this was like age, this was income, other metrics, you could kind of start talking about the differences between the groups and kind of the demographics of them and, why they're separated and kind of what the differences are between the different clusters. And then you can also plot that, just doing bar plots. You can kind of see for each of the features how the clusters differ in their average values. Gives you a good way of like understanding, what's going on underneath all the clustering, especially when you have more than 2 features and you can't just plot it in 2D. So yeah, does anyone have any questions before we go on to an activity? I'll take that as an... Okay, so for the activity, you're going to use customer data in this CSV file from a mall, and you're going to perform market segmentation. using both the k-means and the hierarchical clustering methods. And you'll want to make sure you choose, the best number of clusters for each one. And then you'll kind of do the summary statistics for each cluster for both methods. And you'll want to, in words, kind of write out, the differences between the cluster segments. So, or the customer segments. So customer segment 1 tends to be younger, more male, makes less money, something like that. So that you can kind of put like real world demographic information to the clusters. And then lastly, you'll just kind of think, if you had a new customer with these statistics, which of your segments would you put them into? So the one thing to keep in mind is that with k-means, you can do a predict. So you could predict new points right off the model. With hierarchical, you cannot, but you could look at your mean value statistics for each feature and kind of estimate where you think the new customer would fit into. So that's kind of your goal. You're gonna get to see kind of both methods, maybe see which one's better for this scenario. And yeah, I will go ahead and pause recording.
All right, so the first one that we tried was the k-means clustering, or yes. So just loaded in the data here, took a look, dropped this customer ID column. Next thing we did is we changed the gender column. We just made male equal to 0 and female equal to 1. And so from there, we were able to plot our inertia line here to do the elbow fitting. So we can see here that 4 is really kind of that nice middle point and this kind of elbow part here. So we ended up going with 4. So we fit that here to a k-means clustering model. We use that model to predict our sample person, and we see here that that ends up being the second category with a label of 1. So the next thing we do is we attach the k-means group labels to our data frame. So you can see that here. So now our data frame looks like this. And all we're gonna do is do some group bys to take a look at and validate that it makes sense that he was predicted for that group. And so we do a mean and a median group by here by the k-means grouping. And you can see here that in this label of 1 that our person was predicted to be in, the average age is 32, average income is 86, spending score is 82. When you look at the median values, that gets even closer to our person's, the test person's numbers. So that's the one that we ended up going with, and we thought that made sense. So now we're moving on to the hierarchical clustering. And so the first thing we tried is we tried looking at the dendrogram here. And what we saw was this right here looked like you could have a decent fit for hierarchical clustering. So we ended up having 3 clusters, and considering that we had 4 in the k-means, we thought that made sense. So after fitting that, you can see the different values here. You have 123, 39, and 38. So the next thing we do is we add those cluster group labels to our data frame here. And we do the same thing here. And what we found was that these 2 labels looked relatively similar in age, but the incomes were very different and the spending scores were very different. So the next thing we tried to do is we tried to look at gender as well. And so we do this more sophisticated code in order to incorporate the gender means in there as well. And you can see that although this one leans slightly more female and this one leans slightly more male, the gender doesn't really seem to influence much in these numbers. And so just eyeballing, because you can't do a prediction for the hierarchical clustering, it looks like our person would probably belong in cluster 3. And that's all we got.
All right, cool, thank you. Did the other group do anything differently that you want to kind of show or talk about? Did you pick a different number of clusters for either one?
Yeah, we picked 6.
Do you want to show that real quick?
Sure.
Yeah, I think it's because we included gender in our features. We just one-hot encoded it. Or, yeah.
Yes, so we code gender here, and 1 is male, 0 is female. So in our k-means, we first did a 3, and then from this chart, we picked 6. Yeah, look at the stats and did a prediction, and it tell us it belongs to segment 5, which makes sense. Age 32, annual income 86, spending score 82, and gender is, well, the group is more towards female, but we found out too that gender does not play a big factor there. I wonder if there is any way we can look at each feature and see their impact to the clustering. There's a question.
Give me 1 second, I think there is.
So going down, we did the same thing. We use a k from the k-means. And actually, I think this sample value are pretty good, because if you put anything under 6 here, the one group will be pretty large. So
also, yeah, if you increase the number of clusters above 6, the only thing that's changing are the clusters below the first until you reach about 9 or 10. Then it starts taking people from the first, so it's just getting a bigger dispersion as you increase above 6.
Yeah, but I think it also depends on the business question. So for example, if we're analyzing like Amazon Prime users versus basic users, maybe the basic users will have a much larger size. So I guess it really depends on the business question.
And just to answer your question, Bonnie, there are, I think, a couple ways you could do that. One way to kind of see the importance is to look at the means, like we did in the data frames. So if the mean, is about the same for all the clusters for one of the features, then it's not very significant. I found another thing that said you could actually use the means and use an ANOVA to kind of test the difference.
Yeah, that's a good idea. To see if they make a difference, right?
Yep.
Oh, this is a really good idea. Yeah. So looking at this, I think that this person will be cluster 3.
Which is the same cluster that we got in k-means.
Yeah, the annual income here is a little bit higher than previously, but I still think this is the closest. From this chart, I think age and spending score and annual income make a difference.
Yeah, because gender is like almost always, between 0.4 and
Yeah.
6. So, but it looks like when you broke it down to the 6 clusters, like you do get like cluster 6 is a lot more female.
Younger female, yes.
Mm-hmm.
Yeah,
But yeah.
exactly. And this group will be a older female.
Yep.
Yep.
Slightly more female.
Yeah.
And then about middle income. Yep. So that's kind of how you can, look at the clusters. You can kind of see what they are, so that you can put like, ideas towards these clusters, what kind of groups of people they are. You can imagine if you had a lot more features, a lot more data points, you could really, nail down, this group of people, they're really athletic, they go to the gym, this group works at home, depending on your features, you can really break it down. So
I actually have a work use case if you guys are interested.
yeah, I was going to ask you about that actually, because I know we talked about it a while back and I mentioned like this was coming up. So did you have to use this actually?
I like in the short future. So what we are trying to do is we have a specific segment that we already know. Like for example, there are our existing customers, and we're trying to go find the likely segment based on the features we know about the existing customers. So basically, we want to enlarge that pool so we can target more people. But there are 2 questions. I'm not sure if we are able to answer 2. So the first of all is to identify the enlarged pool. Second of all is to identify actual features. So we already know certain things about the existing customers. Let's say like we already know 10 features, but we are hoping to look at other data sources like third-party data sources and to find another 5 actual features. So I'm not sure if we're able to do that because we don't have any we don't have any independent variable dependent variable to tell us how to rank them, basically.
Okay, so the outside features, like, are those connected to each of your customers?
Yeah, we are able to map them together, use a unique ID. So ideally, each person will be this unique ID, and there are thousands of features about this person. And we want to know what features make them the existing customers or likely existed customers. Does that make sense?
Yeah, I think so. So, I mean, that is a lot of features, but you could probably do something like this, maybe the hierarchical way.
Yeah, so I think like based on the features we know about the customers, we are able to identify like different clusters and identify like other people that also in this cluster, right? Using prediction.
Yeah, so I was talking to Brendan about this, like with the hierarchical, you can't do predict, but you could take the assigned clusters and then basically train a classifier using those labels. And then you could predict on new people using that classifier.
Oh, wow. Is there any resource that you can share with us? Because that would be super helpful for my job.
Yeah, I could find something.
Cool. Awesome.
Yeah.
I'm so glad that I can finally use some of stuff.
Yeah, no, it's good timing.
Yeah, great. Thank you guys. I'll keep you posted the status of this project.
Cool. Yeah, and if you do end up doing it, you should give like a short talk to us on a Zoom call about what you did.
Okay, without exposing other people's information. Sure.
Obviously, yeah. Don't show us anything confidential or anything.
Sure.
So Matt, that brings up a good question here, looking at Bonnie's, because I agree with the 6 clusters, particularly with the hierarchical, you end up with a more even distribution of samples across the clusters.
Mm-hmm.
So based on our analysis of the dendrogram, that's not the number we came to, right? We came to kind of 3. So the question is does evenly distributing the samples matter? Is that a better way to get a more accurate number?
It completely depends on the case. So if you're thinking about detecting like somebody hacking your network or something, then you would probably want, you know, a really large group and then a small group that's the hackers. But if it's a customer base, I think you would probably want them to all be kind of equal, so that you can kind of, I don't know, plan your resources accordingly and, you know, divide it up the best way. So it really just depends. But that kind of cutoff rule on the Dendrogram, it's not like a hard and fast rule. It's kind of just like a suggestion. That's like a good place to start. The elbow method is a little bit more like almost always accurate, but the Dendrogram not so much. So for that, it really comes down to the business case. Yeah, so on the elbow one as well, because the elbow graph we actually had was the same. Because I think the one hot encoding ends up just doing the same thing as just setting them equal to 1 or 0. The difference was they picked one, so there's kind of that inflection in the curve where it levels out. They picked the point at the end right before it levels out, and I picked the one in kind of the middle of that curve. Which one should you ideally pick? So from the name elbow, like it should be, you know, at like the vertice, like where it kind of makes an L shape. But sometimes it's more smooth and there's not like a really obvious choice. In this case, I would have chosen what you did, like at the elbow, but the 6 was still valid. Usually there's like a range. It can kind of narrow it down.
Okay.
And then that also plays into like the business decision, like how many clusters do you want? How big do you want them to be? But yeah, usually just like remember the word elbow, like it's at that point where
Gotcha. All right, thank you.
Yep. All right, does anyone have any questions before we close it out tonight? Did you guys enjoy this?
Yeah, thank you.
Yep.
Cool. All right, well, thanks everyone. Have a good night.
Bye.
Thank you. You too.